Welcome to the IIT PAL problem solving session on quadratic equations. In the series of coming 3 lectures, we are going to solve some problems on quadratic equations. Our questions will be mainly of MCQ types and sometimes we will see more than one options are correct. Also we will see at times a pictorial illustration helps us to solve a problem much easily. We shall start by reviewing the theory of quadratic equations briefly.
By quadratic equation, we mean a polynomial equation of degree 2. And the word quadratic came from the Latin word quadratus, which means made square. So let us first write a general form of a quadratic equation. Ax square plus bx plus c is equal to 0, where a, b and c are complex numbers with a being non-zero. Because note that if a is equal to 0, then the polynomial equation will no more be of degree 2. So we must have a to be non-zero. Now if a is real, then without loss of generality, we can take a to be positive. Because if a is negative, then we know minus of a is positive. So we can multiply the polynomial equation by minus 1 and we would get the coefficient of the term x square in the polynomial equation is positive. This quadratic equation is having exactly two solutions, namely minus b plus minus square root of b square minus 4ac divided by 2a. And I will give a brief hint how to derive that this equation is having these two solutions. Let us call minus b minus square root of b square minus 4ac by 2a as alpha, and minus b plus square root of b square minus 4ac by 2a as beta. So our equation is ax square plus bx plus c is equal to 0. If we take a out, we get x square plus b by a. We can divide by a because a is non-zero, into x plus c by a is equal to 0. So therefore this is same as a into x square plus 2 into x into b by 2a plus b square by 4a square minus b square by 4a square plus c by a is equal to 0. So we have a into x plus b by 2a whole square minus square root of b square minus 4ac divided by 2a whole square is equal to 0. So now if we use the formula of x square minus y square and use the fact that a is non-zero, we get that alpha and beta are the solutions of this quadratic equation ax square plus bx plus c is equal to 0. Now this quantity b square minus 4ac is generally denoted by d, and this has a name. It is generally called the discriminant of the polynomial ax square plus bx plus c. So if we write using the notation d, then we have alpha is equal to minus b minus square root of d divided by 2a, and beta is equal to minus b plus square root of d divided by 2a. Let us make a small note here. if A, B and C are all rational numbers, then we can say if D is a square, then alpha beta are rational numbers. And secondly, if D is not a square, then alpha beta are conjugate surds. Okay. Now let us assume A, B and C, all of them are real numbers, and our standing assumption is A is always positive. So let us note a few facts here. If the discriminant D is strictly bigger than 0, that is if D is positive, then alpha and beta, both the solutions are distinct and they are real. Secondly, if D is 0, then we get alpha is equal to beta, and also they are real. And the last thing, if D is strictly less than 0, that is if D is negative, then we get alpha and beta both are distinct and they are complex conjugates of each other. Let us keep these facts in mind because these facts will be useful for our problem solving sessions. As I said in the beginning, sometimes visualizing something pictorially makes our lives simpler. So now we are going to draw the graph of the parabola y is equal to ax square plus bx plus c, where a, b and c, all of them are real numbers, with a being strictly positive. And we will have three cases here. Let us take our first case to be the discriminant D is strictly bigger than 0. And in every case we will have a number of subcases. Here let us take our first subcase to be B is strictly less than 0 and C is strictly bigger than 0. Now I draw the x-axis. This is our y-axis and the parabola is like this. This is the vertex. Let us call it by P, and this is having coordinates minus B by 2a, comma minus D by 4a. And this is y-intercept 0, comma C. This is alpha and this is beta. So here we can see that alpha and beta both are real and they are distinct. Our next subcase is B is strictly less than 0 and C is strictly less than 0. So this is the x-axis and this is our y-axis, and we draw the parabola here is the vertex P. This is y-intercept. This is alpha. This is beta. So here also alpha and beta both are real and distinct. Now our third subcase is C is strictly less than 0 and B is strictly bigger than 0. So this is x-axis, this is y-axis, and this is the parabola. So this is the point P, which is vertex. This is y-intercept. This is alpha and this is beta. So alpha and beta both are real and distinct. Now I will do one more subcase and leave the rest for you to try. Our fourth subcase is C is strictly bigger than 0 and B is strictly bigger than 0. Now this is x-axis, this is y-axis, and the parabola is like this. So here is our vertex, this is y-intercept, this is alpha and this is beta. So in this subcase also we see that alpha and beta both are real and distinct. Now you shall try this, the corresponding subcases for B is equal to 0 or C is equal to 0. So in the case 1, which is the discriminant D is strictly bigger than 0, we have the solutions alpha and beta both are real and distinct. Now our second case is the discriminant D is equal to 0. Here we take our first subcase to be C is strictly bigger than 0 and B is strictly less than 0. So here is the x-axis, here is the y-axis, and the parabola is like this. So this is y-intercept 0, C, this is vertex P, and alpha and beta are here. The coordinates of the vertex P are alpha, 0, which is same as beta, 0. So in this subcase, alpha and beta both are real and they are same. In fact, we can more clearly write P is having coordinates minus b by 2a, 0. And here alpha is equal to beta is equal to minus b by 2a. Second subcase is C is strictly bigger than 0 and B is strictly bigger than 0. Here the parabola is like this. This is y-intercept 0, C. Here is the vertex P, and here is also alpha is equal to beta. Now our third subcase is C is equal to 0 and B is equal to 0. This is the last subcase in this case because D is equal to b square minus 4ac is equal to 0. That means b square is equal to 4ac. And since b square is always bigger than equal to 0, we have ac is bigger than equal to 0. And as a is always strictly bigger than 0, we get that c is bigger than equal to 0. Now this is our x-axis and this is y-axis, and here the parabola is like this. So this is the vertex P, which is having coordinate 0, 0, and here, so alpha is equal to beta is equal to 0. So in this case we see that the solutions are always real and they are equal. Now we move on to the last case, which is the discriminant D is strictly less than 0. We take our first subcase here to be B is strictly less than 0 and C is strictly bigger than 0. So this is our vertex P, this is y-intercept, and from this picture we can clearly see that there is no real solution, as the parabola is not intersecting the x-axis. So here alpha beta are not real. Okay. Second subcase is B is strictly bigger than 0 and C is strictly bigger than 0. And here the parabola looks like this. So the vertex P is here and y-intercept is here, and here also no real solution. The third subcase is B is equal to 0 and C is strictly bigger than 0. Now let us draw the parabola. So this is x-axis and this is y-axis, and here the parabola is like this. So here is the vertex, which is also y-intercept. So this is 0, C, and here also no real solution exists. Also, let us now note that no more subcases are left, because here D is equal to B squared minus 4AC is strictly less than 0. So therefore B square is strictly less than 4AC. So from here we are getting that C is strictly bigger than B square divided by 4A. Now we know that B square is always bigger than or equal to 0 and A is strictly bigger than 0. So from these two information we can conclude that B square divided by 4A is bigger than or equal to 0, and therefore we have C is bigger than or equal to 0. Therefore we have completed seeing all the cases pictorially. One also studies the sign of the solutions alpha and beta when A, B and C all of them are real numbers. Recall that for D strictly less than 0, we have already seen there is no real solution. So for D strictly less than 0, we cannot study the sign of alpha and beta. We assume D to be bigger than or equal to 0. Let us consider our first case as D is equal to 0. In this case, we have alpha is equal to beta is equal to minus b divided by 2a. So, if b is strictly bigger than 0, then in this case we have alpha and beta, both of them are strictly less than 0. If b is strictly less than 0, then we get alpha and beta, both of them are strictly bigger than 0. And if b is equal to 0, then we get alpha is equal to beta is equal to 0. Now we consider D to be strictly bigger than 0. We know the solutions are minus b plus minus square root of d divided by 2a. Now as a is positive, the quantity 2a is strictly bigger than 0. So for us, it is enough to study the sign of the quantity minus b plus minus square root of d to study the sign of the solutions alpha and beta. Let b to be strictly bigger than 0. So here one of the solutions in particular, which we called as alpha, minus b minus square root of b square minus 4ac divided by 2a is always strictly less than 0. That is, alpha is always negative. So let us look at what happens to the other solution beta. Now if c is also strictly bigger than 0, then d, which is b square minus 4ac, is strictly less than b square. So therefore we get that square root of d is strictly less than b, as d and b both are strictly bigger than 0. So therefore from here we can write that minus b plus square root of d is negative. So therefore beta, which is minus b plus square root of d divided by 2a, is negative. If c is equal to 0, then we have beta is equal to 0, because beta is minus b plus square root of b square minus 4ac. So we have only square root of b square here, divided by 2a. Now we have b is strictly bigger than 0, so we only get minus b plus b divided by 2a, which is 0. If c is negative, that is c is strictly less than 0, then we have d is equal to b square minus 4ac is strictly bigger than b square. So therefore square root of d is strictly bigger than b, as d and b both are positive. Therefore we have now beta is equal to minus b plus square root of d divided by 2a is strictly bigger than 0, that is beta is positive. Now if b is strictly less than 0, then we have the solution beta, which is minus b plus square root of d divided by 2a is strictly bigger than 0, that is the sign of the solution beta is positive. So we have to look at the sign of the solution alpha now. Let c to be strictly bigger than 0. Then here we have d is equal to b square minus 4ac is strictly less than b square. So therefore we can say that square root of d is strictly less than minus b, as d is strictly bigger than 0 and b is strictly less than 0. And from here we can conclude that minus b minus square root of d is strictly bigger than 0. So therefore alpha, which is minus b minus square root of d divided by 2a, is strictly bigger than 0. That is the sign of the solution alpha is positive. If c is equal to 0, then we can see that alpha is equal to 0, because alpha is nothing but minus b minus square root of b square divided by 2a, and as b is strictly less than 0, we get here minus b plus b divided by 2a, which is equal to 0. Now if c is strictly less than 0, that is if c is negative, then d is strictly bigger than b square. So therefore we have square root of d is strictly bigger than minus b, and hence we can say that alpha is strictly less than 0. Now if b is equal to 0, then we know the solutions are plus minus square root of d divided by 2a, and as we have here d is strictly bigger than 0, we can clearly say alpha, which is minus square root of d divided by 2a, is strictly less than 0, and beta, which is square root of d divided by 2a, is strictly bigger than 0. So the sign of alpha is negative and the sign of beta is positive. Now I end recalling the theory part by noting down a few equalities. So we have a quadratic equation ax square plus bx plus c is equal to 0, where a, b and c are all complex numbers. We have sum of the solutions alpha and beta is equal to minus b divided by a. If we sum alpha and beta, we get this is nothing but minus b by a. The second one is that the product of the solutions alpha and beta is minus b divided by 2a whole square minus square root of b square minus 4ac divided by 2a whole square. So this is equal to c divided by a. And the third thing is that the distance between the solutions alpha and beta is modulus of square root of b square minus 4ac divided by a. And the last equality a alpha square plus b alpha plus c is equal to 0, and a beta square plus b beta plus c is equal to 0. Now with all this, we start solving some problems on quadratic equations. In this question, we are given that theta is an angle which is strictly between minus pi by 6 to minus pi by 12. So from here we know that theta lies in the fourth quadrant. We are told that alpha 1 and beta 1 are the solutions of the quadratic equation x square minus 2x sec theta plus 1 equals to 0. And alpha 2 beta 2 are the solutions of the quadratic equation x square plus 2x tan theta minus 1 equals to 0. We are also told that alpha 1 is strictly bigger than beta 1 and alpha 2 is strictly bigger than beta 2. Then our job is to find out what is alpha 1 plus beta 2. And to do that, we have to find out what are alpha 1 beta 1 and alpha 2 beta 2. So we first consider the quadratic equation x square minus 2x sec theta plus 1 equals to 0. And the solutions of this quadratic equation are 2 sec theta plus minus square root of 4 sec square theta minus 4 divided by 2, and this is equal to sec theta plus minus tan theta. Now since theta is in the fourth quadrant, we know that tan theta is negative. Therefore we can say that sec theta minus tan theta is strictly bigger than sec theta plus tan theta. So we now know that alpha 1 is sec theta minus tan theta and beta 1 is sec theta plus tan theta. Next we consider the second quadratic equation, which is x square plus 2x tan theta minus 1 equals to 0. And the solutions of these equations are minus 2 tan theta plus minus square root of 4 tan square theta plus 4 divided by 2, and this is equal to minus tan theta plus minus sec theta. Again, since theta is in the fourth quadrant, we know that sec theta is positive. So therefore, we can conclude that minus tan theta plus sec theta is strictly bigger than minus tan theta minus sec theta. So now we also know that minus tan theta plus sec theta is alpha 2 and minus tan theta minus sec theta is beta 2. So now with all this we are ready to find out what is alpha 1 plus beta 2. We write what is alpha 1 plus beta 2. This is sec theta minus tan theta minus tan theta minus sec theta, which is minus 2 tan theta. So therefore we have now alpha 1 plus beta 2 is equal to minus 2 tan theta. Now we go back to the question. In the question we see that the third option is the correct one. Now we look at this question. We have the set S which consists of all the non-negative real numbers x, so that x satisfies the equation 2 into modulus of square root of x minus 3 plus square root of x into square root of x minus 6 plus 6 equals to 0. We have to find out how many elements are there in the set S, and to do that we shall first note that square root of x minus 3 is bigger than equals to 0 when x is bigger than equals to 9, and square root of x minus 3 is strictly less than 0 when x is strictly less than 9. Now we consider the case x bigger than equals to 9 first. In this case we rewrite the equation. So our equation is 2 into square root of x minus 3 plus square root of x whole square minus 6 square root of x plus 6 equals to 0. So therefore we have the equation square root of x whole square minus 4 square root of x is equal to 0. So this is a quadratic equation in the variable square root of x. As the constant term is 0 here, we can solve it very easily. So this is square root of x into square root of x minus 4 equals to 0. So from here we can conclude that square root of x is equal to 0, or square root of x is equal to 4, and from here we get that x is equal to 0 or x is equal to 16. Now recall that we are in the case x bigger than equals to 9. So therefore x equals to 16 is possible, but x equals to 0 is not possible in this case. Now we consider the next case, that is the case when x is strictly less than 9. And in this case our equation becomes minus 2 into square root of x minus 3 plus square root of x whole square minus 6 square root of x plus 6 is equal to 0. So therefore we have square root of x whole square minus 8 square root of x plus 12 is equal to 0. So again we have a quadratic equation in the variable square root of x. We solve it for the variable square root of x and we get the solutions are 8 plus minus square root of 64 minus 48 divided by 2. So we have square root of x is equal to 2 or 6. So from here we get that x is equal to 4 or x is equal to 36. Now since x is strictly less than 9 in this case, so x equals to 36 is not possible and x equals to 4 is possible. So from here we get only two possible choices of x, that is x equals to 16 and x equals to 4. So therefore we can say that the set S is containing exactly two elements. So therefore the option 2 is the correct one. Here is the third question, and in this question we are given the equation modulus of x square plus 4x plus 3 plus 2x plus 5 is equal to 0, and we have to find out how many real solutions does this equation have. So first we solve this equation for all those values of x for which x square plus 4x plus 3 is bigger than equals to 0, and in this case our equation becomes x square plus 6x plus 8 is equal to 0. Now when we solve this quadratic equation for x, we obtain that x is equal to minus 6 plus minus square root of 36 minus 32 divided by 2, which is same as minus 6 plus minus 2 divided by 2. So we have x is equal to minus 2 or minus 4. Now we shall check that among these two values of x for which the condition x square plus 4x plus 3 bigger than equals to 0 is satisfied. We rewrite the condition here again. X square plus 4x plus 3 is bigger than equals to 0. First we substitute the value x is equal to minus 2 in the quadratic polynomial x square plus 4x plus 3, and we get that 4 minus 8 plus 3, this is equal to minus 1, which is strictly less than 0. Therefore for this value of x, that is x equals to minus 2, the condition is not satisfied. Therefore x equals to minus 2 is not possible. Next we take the value x equals to minus 4, and when we substitute this value in the quadratic polynomial, we get that 16 minus 16 plus 3, and this is equal to 3, and clearly this is bigger than equals to 0. So therefore x equals to minus 4 is possible. Now we solve the equation for all those values of x for which x square plus 4x plus 3 is strictly less than 0, and in this case our equation becomes minus x square minus 4x minus 3 plus 2x plus 5 is equal to 0. That is, we have x square plus 2x minus 2 is equal to 0. So we solve this quadratic equation now, and we obtain that x is equal to minus 2 plus minus square root of 4 plus 8 divided by 2, and this is same as minus 2 plus minus 2 square root of 3 divided by 2. So we have x is equal to minus 1 plus minus square root of 3. Now among these two values of x, minus 1 plus minus square root of 3, we shall check for which the condition x square plus 4x plus 3 strictly less than 0 is satisfied. First we consider x is equal to square root of 3 minus 1. So when we substitute this in the quadratic polynomial x square plus 4x plus 3, we obtain that 3 minus 2 square root of 3 plus 1 plus 4 square root of 3 minus 4 plus 3, and this is same as 2 square root of 3 plus 3, which is strictly bigger than 0. So therefore x is equal to square root of 3 minus 1 is not a solution. Then we consider x is equal to minus 1 minus square root of 3. So when we substitute this, we obtain that square root of 3 plus 1 whole square minus 4 into square root of 3 plus 1 plus 3. This is same as 3 plus 2 into square root of 3 plus 1 minus 4 into square root of 3 minus 4 plus 3, and this is same as 3 minus 2 into square root of 3, and clearly this is strictly less than 0 as 12 is strictly bigger than 9. Therefore x is equal to minus 1 minus square root of 3 is possible. So we get that this equation is exactly having two real solutions. So the third option is correct here. In this question, we are given the equation e to the power sin x minus e to the power minus sin x minus 4 is equal to 0. And as it is evident from the options, we have to find out how many real solutions does this equation have. So we write the equation e to the power sin x minus e to the power minus sin x minus 4 is equal to 0. And this is same as writing e to the power 2 sin x minus 4 into e to the power sin x minus 1 is equal to 0. So we see that this is a quadratic equation in e to the power sin x. For simplicity, we put y is equal to e to the power sin x. So we have this quadratic equation y square minus 4y minus 1 is equal to 0. So when we solve it for y, we obtain that y is equal to 4 plus minus square root of 16 plus 4 divided by 2, which is same as 4 plus minus 2 square root of 5 divided by 2, and this is same as 2 plus minus square root of 5. First we show that y cannot be equal to 2 minus square root of 5. So for that, first we note that 2 minus square root of 5 is strictly less than 0 as 4 is strictly less than 5. Now for any real number x, sign of x is always real, and as we know, for any real number x, e to the power x is always real, and in fact it is strictly bigger than 0. So therefore e to the power sin x is strictly bigger than 0 for any real number x. So here, as y is equal to e to the power sin x, so y cannot be equal to 2 minus square root of 5, as 2 minus square root of 5 is strictly less than 0. So the only possible choice for y is equal to 2 plus square root of 5. Now we write what is y. This is e to the power sin x. So we have e to the power sin x is 2 plus square root of 5. We take logarithm to the base e on both sides of this equation, and therefore we obtain sin x is equal to logarithm of 2 plus square root of 5. Now 2 plus square root of 5 is strictly bigger than 4, and we know 4 is strictly bigger than e. So therefore logarithm of 2 plus square root of 5 is bigger than logarithm of e, as logarithm is an increasing function, and we know that logarithm of e to the base e is equal to 1. So therefore we are getting that sin x is strictly bigger than 1, which is not possible, as we know that for any real number x, sin x is always bigger than equals to minus 1 and less than equals to plus 1. So therefore sin x bigger than 1 is not possible. So we get that this equation is not having any real solutions. This is our fifth question. In this question we are given three positive real numbers p, q and r which are in an arithmetic progression. Also we have this quadratic equation px square plus qx plus r is equal to 0. We have to find out the conditions on p and r for this quadratic equation to have all real solutions. First note that q is equal to p plus r divided by 2, because we are told that p, q and r are in an arithmetic progression. Now as we know, the necessary and sufficient condition for the quadratic equation px square plus qx plus r is equal to 0 to have all real solutions is q square minus 4pr is bigger than equal to 0. So when we substitute the value of q, which is p plus r divided by 2 in this condition, we obtain p plus r whole square minus 16pr is bigger than equal to 0, which is p square minus 14pr plus r square is bigger than equal to 0. Now since p is a positive real number, we know that p is non-zero. So therefore we can divide this inequality by p square and we obtain 1 minus 14r by p plus r by p whole square is bigger than equal to 0. We now rewrite this inequality r by p whole square minus 2 into r by p into 7 plus 49 is bigger than equal to 48. So therefore we have r by p minus 7 whole square is bigger than equal to 48. So therefore we can conclude that modulus of r by p minus 7 is bigger than equal to 4 square root of 3. So we can see that the fourth option, modulus of r by p minus 7 is bigger than equal to 4 square root of 3 is correct. Now let us check the other three options. To do that, let us first find out the location of the ratio r by p. So we can write from this inequality that r by p is bigger than equal to 7 plus 4 square root of 3, and also we can write minus r by p plus 7 is bigger than equal to 4 square root of 3, which means r by p is less than equal to 7 minus 4 square root of 3. So from here we can now locate where does the ratio r by p belong to. Since r and p both are positive numbers, the ratio r by p is positive. So r by p belongs to open 0 to closed 7 minus 4 square root of 3 union closed 7 plus 4 square root 3 to infinity. Now observe that when the ratio r by p is in the interval open 0 to closed 7 minus 4 square root of 3, then the ratio p by r is in the interval closed 7 plus 4 square root of 3 to infinity. And when the ratio r by p is in closed 7 plus 4 square root of 3 to infinity, then the ratio p by r is in the interval open 0 to closed 7 minus 4 square root of 3. So from here now we can say that the condition modulus of r by p minus 7 is bigger than equal to 4 square root of 3 is equivalent to modulus of p by r minus 7 is bigger than equal to 4 square root of 3. So the option 3 is also correct. Now in the process, as we have seen that we are getting possible choices for the ratios p by r and r by p in certain intervals. So the option 1 and option 2 are not correct. So this solves the question 5. Here in this question we are given 3 positive real numbers a, b and c, which are the lengths of the sides of a triangle, and also we are given one real number lambda and the quadratic equation x squared plus 2 into a plus b plus c into x plus 3 lambda into ab plus bc plus ca is equal to 0. We are to find out the range of lambda for which this given quadratic equation is having all real solutions. Now to do that, we shall first write down the necessary and sufficient condition for this quadratic equation to have all real solutions. And the condition is 4 into a plus b plus c whole square minus 12 lambda into ab plus bc plus ca bigger than equals to 0. Now if we cancel 4 from this inequality and if we split this term a plus b plus c whole square, we obtain that a square plus b square plus c square plus 2 into ab plus bc plus ca minus 3 lambda into ab plus bc plus ca is bigger than equal to 0. So therefore finally we obtain 3 lambda minus 2 is less than equal to a square plus b square plus c square divided by ab plus bc plus ca. Now we use the information that a, b and c are the lengths of the sides of a triangle. So therefore a plus b is strictly bigger than c and a plus c is strictly bigger than b and b plus c is strictly bigger than a. So we have these 3 inequalities. Now from the first inequality a plus b is strictly bigger than c, we can write that a is strictly bigger than c minus b and also b is strictly bigger than c minus a. From the second inequality we can write that a is strictly bigger than b minus c and c is strictly bigger than b minus a. And from the last one we can write that b is strictly bigger than a minus c and c is strictly bigger than a minus b. Now let us consider this inequality that a is strictly bigger than c minus b and the inequality a is strictly bigger than b minus c. So from these two we obtain that a is strictly bigger than modulus of C minus B. Next we consider this inequality that B is strictly bigger than C minus A and the inequality that B is strictly bigger than A minus C. So from here we obtain that B is strictly bigger than modulus of C minus A, and from the last two remaining inequalities we obtain that C is strictly bigger than modulus of B minus A. Now we are going to use all these three inequalities, and what we will do is that we will square both sides of these inequalities. Then we get A square is strictly bigger than B square plus C square minus 2BC, and B square is strictly bigger than A square plus C square minus 2AC, and C square is strictly bigger than A square plus B square minus 2AB. Now we add all these three inequalities. Then we obtain A square plus B square plus C square is strictly bigger than 2 into A square plus B square plus C square minus 2 into AB plus BC plus CA. So therefore we have A square plus B square plus C square divided by AB plus BC plus CA is strictly less than 2. Now recall that we already had that A square plus B square plus C square divided by AB plus BC plus CA is bigger than equals to 3 lambda minus 2. So therefore we can say that 3 lambda minus 2 is strictly less than 2. So therefore lambda is strictly less than 4 divided by 3. Hence the first option, that lambda is strictly less than 4 by 3, is correct. So therefore the second option, that lambda is strictly bigger than 5 by 3, cannot be correct. And also at the same time we can say that the fourth option, that lambda is in the open interval 4 by 3 to 5 by 3, is also not correct. So we have to only check whether the third option, that is lambda is in the open interval 1 by 3 to 5 by 3, is correct or not. To check that, let us put lambda is equal to 0 in the given quadratic equation, and putting this we obtain that x square plus 2 into a plus b plus c into x is equal to 0. And clearly we can see that this quadratic equation is having all real solutions, as a, b, c are real numbers. So therefore the third option is also not correct. As we see, for 0, that is for lambda is equal to 0, this equation is also having all real solutions, but 0 is not in this open interval 1 by 3 to 5 by 3. So here only one option is correct, which is the first option, that is lambda is strictly less than 4 by 3.
We end our first session here. Today we have reviewed the theory of quadratic equations, and using that we have solved some problems. In the next two lectures we will solve some more problems.